Okay, so welcome back. We're going to get started with the third session. We're going to have 4 paper presentations. First, Lasse Borholt, and second, Juliette Miet, and third, Woo Hyun Kang, and fourth, Sri Harsha Dumpala. And we will do 10 minutes each, and then there will be 10 minutes at the end for questions. So save your questions. You can put them in the chat. And then the speakers will be able to reply to them at the end. So let's get started first with Lasse Borholt, a brief overview of unsupervised neural speech representation learning. Take it away.
Thank you very much. Hi, my name is Lasse Borholt, and I want to present our paper, a brief overview of unsupervised neural speech representation learning, which today can be boiled down to a 10-minute overview. So of course, this is a lot to cover in 10 minutes, so we'll just jump right into it. We'll start out with a little definition, although you all probably know what representation learning is. So representation learning is concerned with learning representations of the data that make it easier to extract useful information when building classifiers or other predictors. So with this definition, you can see that representation learning ties quite naturally with improving some downstream task. In this overview, we distinguish between 2 overall model categories: self-supervised models and latent variable models. So latent variable models have a quite standard structure where we use an encoder or an inference model to map the observed variable x to a latent variable set, and then we use a observation model or decoder to map the latent variable back to the observed, or to reconstruct the observed variable x. So it's a bit more fuzzy for self-supervised models. We use a notation where we take a function f to encode the input x to a typically contextualized representation, and then we can use one or more auxiliary functions g to support the self-supervised task, for example, to infer a learned target. Yes. So we start out by defining a general model taxonomy, which consists of some binary attributes divided into 3 categories. So the first 4 here can sort of be viewed in this matrix format, where we distinguish between either predictive or masking-based models, or contrastive or reconstructive models. So a predictive model is simply a model that predicts future values from previous values, and a masking-based model is a model that use masking to define the target region for the self-supervised task. Reconstructive models are models that simply use the input as the target, whereas contrastive models will typically use a learned representation, which makes it necessary to use a contrastive loss with negative sampling. Of course, there are very recent work like Schubert and Data to Beck, which does not rely on the contrastive loss despite learning a target. So here are some examples that you may or may not know in each of these categories. Another attribute that we use is quantization. So quantization is a popular design choice and can be used for many different motivations. It can be used as a regularization to limit the model capacity. It can be used to learn a segmentation of the input speech by taking consecutive quantized representations of the same value to belong to the same segment. It can be used in order to apply NLP models like BERT, and it can be used to learn a quantized target. In addition, there's different approaches to do quantization. A fully differentiable way is the Gumbel softmax, where we directly parameterize and sample a categorical distribution, and the VQVE approach, as we have dubbed it, where a vector is mapped to a codebook, and then we add some auxiliary losses to support learning this quantization during the representation learning task. Then there's also good old k-means, which is used in, for example, Schubert, which permits learning a target, and we do not have to rely on a contrastive loss, but can rely on a regular classification loss. We also have an attribute here related to whether a model is generative or not. So we use a quite strict definition of generative models, which means that the model have to have a well-defined generative process that allows to sample new data points. This includes latent variable models, which we have included in this review, but also like autoregressive models and flow-based models, which are not included. Then we have models, then we have some attributes related to the temporal resolution of the learned representation. We distinguish between 3 different categories here. We have local representations where the model learn representations that are proportional to the input resolution. Then we have global representation models, which just outputs a single vector regardless of the length of the input. These models are also sometimes referred to as embedding models. And then we have variable rate models, which basically learns an implicit or explicit segmentation of the input, and it cannot be set a priori how many outputs the model will yield. Then finally, we have some attributes related to how the model is adapted to the downstream task, where we can either distinguish between feature extraction from a frozen model or fine-tuning of the entire representation model or the parts of the representation model. So we apply these attributes to a selection of models here, and then we can get a table like this. So a few things we want to highlight here is that these attributes are pretty well suited for describing the self-supervised models in this overview. We can see these attributes can be combined in different ways. In terms of the resolution of the self-supervised model, we see that the global models tend to precede the local models, although we do see some of the same modeling techniques having been used in earlier work. For the probabilistic latent variable models, which has not been as successful as the self-supervised models, these binary attributes are not as well suited for describing. In fact, we can see here that 4 of the columns is given by definition of the latent variable model framework. Latent variable models cannot be predictive or contrastive, and they will always reconstruct the input and be generative. But on the other hand, these models have the interesting feature that they can learn local and global models simultaneously. Well, self-supervised models can also do this, but none of the models that we covered in our overview use this feature. Then finally, with regard to how these models are adapted to the downstream task, we see that it's by far the most popular choice to extract representations, although it's getting more common to fine-tune these models. And of course, a lot of these models can also be fine-tuned, although the authors didn't do it in the original work. But this can simply be a matter of computational demands or that it's more interesting to actually probe the learned representations for certain features. So because the probabilistic latent variable models were not super well described with the attributes we just defined, we also defined a separate taxonomy for these models. Here we focus on the relationships between the observed and the latent variable and between different time steps. And we can divide this into sort of design choices for the observation model or the decoder, the prior, and the inference model, also known as the encoder. And again, we end up with a model taxonomy as the one we just saw. It's a bit more difficult here to extract some trends from this overview. So let's focus on some of the the attributes here that we outlined before. So one common choice is to use an autoregressive dependency on the observed variable in the decoder. This is tremendously useful for generative modeling, but the question is if this is also a good idea for representation learning. Basically, you could argue that it would encourage the model to discard information that can be learned from previous time steps from a given latent representation. And it's typically the latent representation set that is used as input for downstream tasks when these models are evaluated. Then we also have, it's also quite common to use an autoregressive prior. Again, this is important for generation, otherwise we cannot generate meaningful output, but it's a question whether this is useful for representation learning. I can see we're a bit short on time here, so I can see, with regard to these models also, as I said before, well suited for learning both local and global representations, especially because they are punished by the KL divergence if they repeat the same information. So this basically forces these models to separate the information into global and local representation if you use a hierarchical model this. And finally, I just want to relate some of the design choices used for these models to the self-supervised models we saw before, where we can say that some models depend on previous outputs, like, for example, APC. Some models depend on a limited receptive field, like a non-autoregressive predictive coding, NPC. And a few models also use the entire input to learn the representations, which is also quite common in self-supervised learning, where we see transformers being used to a wide extent. But this has not yet become very popular for latent variable models. So this was all what I could squeeze into this 10-minute overview of neural speech representation learning. Thank you.
Okay, thanks very much. We're going to move right on to the second presentation. Juliette. Good. Okay. So the next presentation will be Juliette Millet, who will present the self-supervised speech models to develop human-like perception biases. Go ahead.
So hi, everyone. So yeah, I'm going to present to you this work I did with Yuan Dumba, that is also here, who is also here. So in recent years, there have been great progress in speech recognition. And as you may all know, this is mainly due to the use of self-supervised models. So what we do with them is that we're going to train them in a self-supervised way. So just exposing them to speech recordings. And after that, they're going to develop a relevant representational space. And after that, we're going to fine-tune them on the task of speech recognition in order to map this relevant representational space to characters. What we are interested in this paper is the representational space that these models develop during the self-supervised training. So in order to understand what we're going to do to study this representational space, first you need to know that as humans, we are influenced by our native language. So we have biases in our perception that are influenced by our native language. And this is particularly salient when we listen to non-native languages. So the classic example of that is the example of Japanese native speaker who, when learning English, will struggle differentiating the sound R and the sound L. So the word right and light in English are going to be really similar to them. On the contrary, when you take all the sounds in English, like in R, Japanese native speaker it will be really easy for them to discriminate those two sounds. So troop and trap are going to be different words. On the other hand, if you take an English native speaker, of course, he or she will be able to discriminate the contrast roller and the contrast UA really easily. So these are small examples of native languages biases, but actually you can study that kind of phenomena on a really large scale, and that's what we did. So we created a human benchmark that is called Perceptimatic, which is available on the web using this address. And this benchmark contains the results of discrimination tasks of French-speaking participants and English-speaking participants for more than 600 phone contrasts in 6 different languages. So what we ask participants to do is perform ABX tests. So for one atom, what these participants are going to do is just listen to 3 sounds in a row. So here, for example, first a sound A, pop, then a sound B, pap, and then a third sound, pop. X, and the participant is going to say which of the first 2 sounds is the closest to the last sound he or she heard. And here the right answer would be A, of course. And this enables us to know if the participant can tell the difference between O and A. Okay, so the question we have in this work is, we know that as humans, we are influenced by our native language. Is the same thing happening for self-supervised models with their training language? Do self-supervised speech models develop human-like perception biases? And we actually have 2 sub-questions relating to that. The first one is, do they reproduce human discrimination behavior when exposed to the same language? And the second question is, does a change of trained language has the same impact as a change of native language for humans? So in order to answer these two questions, we need to produce discrimination results, to extract a discrimination result from self-supervised models and from models in general. And for that, we're going to use previous methods we developed in previous work. So we're going to, for each item in the discrimination task, we ask participants to do, we're going to extract the stimuli in it. So here, the pop, pap, and pop that I previously talked about. And we're going to compute distances between these representation. So these representation, of course, are extracted from the models. And then we're going to assume that the discrimination results of the model is what we call a delta value, which is the difference between the distance of the wrong answer, between the wrong answer and X, so here between X and B, minus the distance between the right answer, so here A, and X. And so the bigger this value, the better the model is at doing the ABX stacks for this particular triplet. So we're going to test multiple self-supervised model. So we're going to test a CPC model, a really simple one. Then we're going to test wave2vec, UBIT, and we're going to train them on English and French, since this is the native language of the participants we tested. We're also going to train them on acoustic scenes, so sounds in everyday life, but not produced by humans, in order to see what is the impact of training them on speech compared to non-speech. We're also going to have two references, a baseline, simple acoustic features and FCCs, and a top line, so deep speech trained to perform phone recognition on English and French once again. So French models are going to predict French, the result of the French participants, and English models are going to predict the results of the English speaking participants. Okay, so the first question was, can self-supervised models predict human discrimination behavior? We have two metrics in order to evaluate that. The first one allows us to evaluate the similarity between models and humans at the stimuli level. So it's the log likelihood of a probit model that tries to predict from the delta values of the models the result of the participants for each individual stimuli. And the second metric we have is more global. It's a simple Spearman correlation between the average result per contrast for the models and the average result per contrast for the humans. So this allows us to have a global metric. And this is the result we obtain. So on the first line, you've got the result for the log likelihood. So the smaller bar, the better. On the second line, you've got the result for the Spearman correlation. So the bigger bar, the better. And you've got a result for the French participants on the left, result for the English participants on the right. The speech, the models trained on speech are in light gray, and our references and models trained on acoustic scenes are in darker gray. And we've got the top line in white. So what you can see, if we focus on the stimuli level evaluation, is that models are actually quite good at predicting human discrimination behavior at the stimuli level. They're even better than our top line. And they are better than MFCCs. And when they are trained on acoustic scene, on the contrary, they are, of course, worse and worse than MFCCs. If we now focus on the contrast level, what you can see is that it's actually quite inverted in terms of results. So the speech, the models trained on speech, so not something, are actually worse than MFCCs. And the best model to predict human discrimination behavior at the contrast level is our top line, so the deep speech model. And the models trained on acoustic scene are still worse than the one trained on speech. Okay, so the second question we had was, can model reproduce differences in human discrimination behavior? So can they predict the difference in discrimination behavior between two language groups? So in order to evaluate that, what we're going to do is that we're going to average the result for the models and for the humans at the contrast level. And then we're going to compute the difference between French and English for the participants and French and English for the models. And we're going to plot the result for each contrast. So here, this is what's represented on the screen. And once we plotted all the contrast, if there is a correlation, it means that the model managed to capture some kind of a native language effect. It can predict the difference in behavior between the French and the English group. But if there's no correlation, it means that there's no native language effect. So this is the result we obtained. So it's just the correlation we obtained for the different models that were trained on French and English, with in white the result of our top line. And what you can see is that the correlation we obtained for the whole perceptimatic benchmark, the correlation are quite low, even for top line, but actually, but you can still see that the Wave2Vec and Hubert obtain smaller correlation than CPC. And if we focus on a subset of the perceptimatic, which was created especially to capture the different discrimination behavior for the French and for the English group, we can see that our top line is actually quite good at capturing the native language effect here. And we still see this difference. CPC is better than Wave2Vec and Hubert to do that. The correlation obtained by Wave2Vec and Hubert are quite low. Okay, so in conclusion, self-supervised models can predict human discrimination behavior at the stimuli level, but not very well at the contrast level. They need to be trained on speech to do that. And they show a very small native language effect, except for CPC. And that's it. Thank you.
Okay. Thanks very much. Again, you can write your questions in the chat and we can come back to them at the end. The next presenter, Woo-Hyung Kang, can you put your slides up? Just hit share screen.
Yeah, just a second. Can you see my screen?
Yes.
Okay, great.
Okay. So next presenter will be Woo-Hyung Kang, investigation on instance mix-up regularization strategies for self-supervised speaker representation learning. Go ahead.
Yeah, hello, my name is Woo-Hyung Kang from the Computer Research Institution of Montreal. And in this presentation, I'll be sharing our investigation on iMix regularization for self-supervised speaker verification. So why do we need self-supervised speaker representation learning, or more specifically, self-supervised speaker verification? Nowadays, we can collect vast amounts of speech data from various mediums for training a speaker verification system like YouTube or SoundCloud. However, most of these speech samples scrabbled from the net they don't have any speaker labels. And also collecting speaker label speech samples can be very expensive in terms of resource and time. And the conventional speaker embedding systems, they showed impressive performance in various speaker verification tasks. However, since they're formulated in a fully supervised manner, most of them require speaker labels to be trained. Therefore, it is important for us to utilize some kind of a pseudo label to apply these conventional framework to the self-supervised scenarios. For example, for a end-to-end speaker verification system, for training it, we usually use a contrastive objective function. And for contrastive objectives, we need to define the positive pairs and the negative pairs of the training set. And for a self-supervised scenario, one way to achieve this is to consider the utterance identity as the pseudo labels. So for each training samples, we can apply two different types of augmentations. So this will result in two different samples per training utterance. So after this, we can consider the samples created from the same utterance as positive pair and the rest as negative pairs. And this way we can apply the contrastive loss functions to a self-supervised scenario. So by using a pseudo label for training the speaker verification system, it can allow us to train the system without any speaker label. However, the performance is very limited as the pseudo labels are not actual speaker labels. So as you can see in this graph, which is the validation equal error rate of two systems, one trained with true label, which is the fully supervised system, and one trained with the pseudo labels. So as you can see, while the true label system, the performance increases as the training proceeds. However, for the pseudo label system, in the beginning, the performance increases, but it quickly degrades as the training proceeds. So from this result, we can see that as the system is optimized more to the pseudo labels, it is likely for the system to learn unwanted information. So one way to overcome these kind of unwanted overfitting problem is the mix-up strategy, or more specifically, the instance mix-up strategy. So the iMix or instance mix-up is a data-driven augmentation strategy for improving the generalization of a self-supervised representations. And so basically iMix is identical to the standard mix-up algorithm, but instead of dealing with true labels, iMix deals with pseudo labels. So given a pair of input samples and pairs of corresponding pseudo labels, the iMix creates a new training sample by interpolating the input samples, and also using the same coefficient for linear interpolation, they interpolate the pseudo labels. And for cross-entropy based loss functions like prototypical loss, this equation can be rewritten as follows. And so essentially, iMix creates synthetic training samples with new pseudo identities. And for the lambda coefficient for linear interpolation, iMix uses the same method as in the standard mix-up strategy, where the lambda is randomly sampled from a beta distribution. So it's going to have a value between 0 and 1. And depending on the alpha parameter, the beta distribution and the sample lambda will have a very different behavior. So to enhance the generalization of the self-supervised speaker verification system, we can apply the iMix strategy to the conventional angular prototypical objective, which is basically interpolating between the input acoustic feature like MFCCs and also their utterance identity pseudo labels. So applying iMix strategy for self-supervised speaker verification training is, we believe that it will bring a lot of performance improvement, because the mix-up augmentation, it has proven its strength in various tasks such as speech recognition or image classification. However, we think there is room for improvement. And one of the biggest limitations we think is the linear interpolation. Due to this linear interpolation and the mix-up strategy, the iMix strategy can only generate new samples on the line between the original samples, and which may restrict the diversity of the synthetic training samples, and also thus may limit the generalization of the overall system. In order to overcome this limitation, in this paper, we proposed a new mix-up strategy called LMix, which is basically an iMix strategy applied on the latent space. So in order to extract the latent variable, we used a variation autoencoder. And prior to training the embedding system, we first train a VAE for reconstructing the acoustic features, in our case, the MFCC features. So once the VAE is trained, we can use this VAE for extracting the latent variable for mix-up and also reconstructing the acoustic feature. So using the VAE encoder, we can extract the latent variable from each training samples in the pair, and we can interpolate the latent variables. And with this mixed latent variable, we can feed the mixed latent variable into the VAE decoder to generate a synthetic acoustic feature. So basically, it's the LMix is operated in the same way and with the conventional iMix framework, but the main difference is that unlike iMix, which interpolates on the feature space, the LMix interpolates in the latent space and then projects it back to the feature space using a nonlinear method. In order to validate our system, we used the Voxelab dataset, where the systems were trained using Voxelab 2 development set and evaluated on the Voxelab 1 original trial set. And the acoustic feature we used was 40-dimensional MFCC, and we used other types of augmentations like wave level augmentation, like Muson noise or RIR simulation. And also we applied Kepstrom level augmentation, which is basically spec augment, but instead of applying it on the MEL spectrogram, we applied it to the MFCC directly. And for the embedding system, we used the kappa TTNN, And for the latent variable extraction, we used a 10-layered convolutional VAE. So in our first experiment, we analyzed the synthetic samples created from the IMIX and the LMIX. And as you can see in the figure, so these two synthetic samples are created using the same coefficient, lambda coefficient. And as you can see in the figure, since the IMIX and LMIX applies mix-up on different spaces, they can create very different samples, even though if they're using the same coefficient, which tells us that the LMIX and IMIX, they will create synthetic samples with very different behaviors. And this is more apparent in the feature space so since the IMIX strategy applies linear interpolation on the feature space, as I mentioned in the beginning, the generated samples are bound to be placed on the line between the two original samples. So if you see the distance between the line and the IMIX synthetic samples, they're basically zero, they're on the line. But on the other hand, the samples created by LMIX are not necessarily placed on the line, which indicates that the LMIX may create samples with more diversity on the feature space. So in our next experiment, we compared the speaker verification performance of different systems trained with different types of regularization techniques. So as you can see, compared to AP, which is a system trained with no regularization at all, the IMIX and LMIX both were able to improve the performance when the right coefficient was used. However, the best performance was observed when the LMIX was used, moreover with the wave level augmentation and Kep's augment, which tells us that LMIX is a very effective way for improving the generalization of the self-supervised speaker verification system. So in conclusion, in this paper, we incorporated the IMIX strategy for self-supervised speaker verification. And we also proposed a latent variable IMIX strategy, which basically performs IMIX on the latent space of the speech. And our experimental results show that the self-supervised speaker verification system can benefit greatly by applying the IMIX regularization strategy. And moreover, the proposed LMIX strategy could further improve the performance, perhaps attributed by the diverse synthetic samples created by the LMIX. Thank you for your attention, and that's all for my presentation.
Okay, great. Thanks very much. Would the next speaker line up their slides? Well, again, any questions, we can save them till the Q&A at the end after the speaker. So the last presentation of this session before the Q&A will be, you can throw your slides back up.
I'm sorry for that, just coming.
There you go. Okay.
Can you see me?
Yeah, we got it now. Okay, so the last presentation will be detecting depression with the temporal context of speaker embeddings by Sri Harsha Dumpala. Okay, go ahead.
Hello, everyone. I'm Sri Harsha, and today I'll be presenting the paper detecting depression with a temporal context of speaker embeddings. And the motivation for this work is mental health disorders are a leading cause of disability, and in both because of both mental and physical disabilities. And according to WHO, more than 300 million people suffer from just depression. So, and one of the key methods to treat depression is early diagnosis, and clinical-based assessment is generally time-consuming and very expensive. So automatic mental health assessment techniques are very useful to mitigate this problem. And the automatic mental health assessment could be helpful for screening individuals before they visit the mental health system. This is to help people with stigma and also assist clinicians in making a better decision and to monitor symptoms during the treatment purpose. And because of these advantages, many machine learning methods were used for automatic detection of depression, and many modalities were used like speech, text, and vision. Here we will confine to the speech. And speech is the primary source of information which the clinicians generally consider for predicting people with depression analysis. And psychiatric analysis based on speech mostly was confined to supervised learning techniques, but the performance of these techniques is not so good because of the availability of data. So as self-supervised learning techniques have attained a lot of attention in the recent times, in this paper, we tried to see, can we use self-supervised embeddings to improve the detection of depression? And particularly, we will use the speaker embeddings, and we will also compare with other self-supervised speech embeddings performance. And the main questions of interest we are going to ask in this presentation are, do the speaker characteristics change based on the variation in depression severity score? That is, when the self-supervised learning method, speaker embedding method was trained, and if we extract the speaker embeddings, does the speaker embeddings change when the depression severity of a subject changes? And can the speaker embeddings, which are models which are trained on very large set of speakers, and then the speaker embeddings extended from these models be used for depression detection? And the third one is, if we take the embeddings from a pre-trained model and then combine them with the acoustic features, do they carry any complementary information? And in this, we initially pre-train a model for speaker classification. So this is a model where we provide the spectrogram as input, and we train the model on the similarity loss, where using the contrast to loss, where we project all the embeddings of the same speaker to a close by space, and the embeddings of different speakers to a farther place. And in this work, we have trained the model on work setup dataset, which is a very huge dataset for the speaker classification task. And then once the network was pre-trained, we extract the embeddings from this network for further analysis on the depression dataset. So the first question we are asking is, will the speaker embeddings, which are trained on a very huge dataset, when used for extracting speaker embeddings from speakers, for the same speaker with different depression severity scores, does these embeddings change? So in order to answer this question, we considered a longitudinal data where the data was collected from 100 different speakers. And for each speaker, we collected data at 2 different instances of time, and with a separation of 8 to 16 weeks. And then at each point of time, the depression severity score of the speaker was different. So now we plotted the cosine similarity score between the speaker embeddings obtained at different longitudinal samples. And we plotted them across the difference in the depression severity score. For instance, if a speaker has a depression score of 5 on one day and 6 on one day, so the variation in the depression score is 1. And we extracted the speaker embeddings of both the samples, and we computed the cosine similarity scores between those samples to see how the speaker embeddings extracted from these samples change based on the variation in the depression severity scores. And as can be seen from the plot, as the variation in the depression severity increases, the speaker embeddings, the similarity between the speaker embeddings reduces as the cosine similarity is being reduced. So this provided us with the motivation that yes, speaker embeddings do capture some depression specific information, which can, so once we had this, now can these embeddings be used for depression detection? So given the speaker embeddings, we trained a model, and here the context is the segments, a sequence of segments, and we trained a model. And then we considered 2 different data sets. One is a public data set and the other one is an internal data set. And they were rated on PHQ-8 and Madras scores. And if we see the depression detection performance, we can see that the models which are the speaker embeddings when trained on different models achieve state-of-the-art performance. And we compared this with previous other self-supervised learning techniques like trail, VQ, wave-to-wake, wave-to-wake 2.0, Mockingjay, and the speaker embeddings. And we can see that the speaker embeddings do perform better than the other self-supervised learning techniques, showing that the speaker embeddings do capture some depression-specific information. And the third question we had was, does the speaker embeddings extracted from pre-trained model carry complementary information compared to the acoustic features? And to achieve this, we just added the speaker embeddings with the acoustic embeddings, and then we train models to see how the performance is there. And we see there is an improvement in performance, showing that the speaker embeddings do carry complementary information compared to acoustic features. And finally, we also consider the temporal context, which shows that the higher the amount of speech we have, the better is the performance. And conclusions, yes, there are variations in speaker embeddings when the depression severity score changes. And speaker embeddings do carry a complementary information to acoustic features. And speaker embeddings can be used for depression detection. Thank you, and any questions?
Okay, thanks very much, and thanks to all of our 4 speakers. So yeah, let's start the Q&A. So we have 10 minutes for questions. Any questions for any of the 4 presenters? We can share the slides. Which one are you looking for? The most? There's a comment in the chat. Please share the slides. Is this the last one? Okay, so I guess we got a question about the last presentation. Can you share the slides again? I can't hear.
I will share them. Yes.
Yeah, go ahead.
Yes.
Okay. Is this what you're looking for? So we've got a question about this. Maybe not. Yeah, okay. That's a question for a different one. Okay, so we thought we had a question from Vivek, but I'm not sure whether there's a question about it. So maybe we can come back to that. Next, we have a question from Karen for Juliette. Juliette, do you want to? Sorry about that, Juliette. Do you want to read your?
Yeah, so the question is, do you know how much the results differ if you vary certain design choices in DTW, so dynamic time warping, path constraints, frame similarity function, or even use a non-DTW based similarity function? So I try, so the similarity function used here for the distance used in the dynamic time warping is cosine similarity. So I try with Euclidean distance instead, and it doesn't change the results. So the tendencies are the same. And I'd also try using like a Gaussian sum of instead of using dynamic time warping, I like do an average of the sequences of the different items I use in the ABX triplets. So just like you have the sequence and you just do a sum following a Gaussian, and you use these average representations to compute distance between A, B, and X. And the results were better using this Gaussian, but the tendencies were still the same. So this change between the metric at the stimuli level and at the contrast level, and the order, like the performance of the model, the order of performance was still the same. So I tried these 2 other methods, but it would be interesting to test others. Maybe there's a dependency that I didn't check. So yeah, maybe.
Yeah, great. Okay, sorry, I misunderstood the previous question. It wasn't share the slides in the Zoom, it was share the slides let's share the document. Yeah, but we will be collecting the slides from speakers and putting it on the workshop website. Okay. Are there other questions about any other presentations? We still have 5 minutes. I had maybe a question for the first presenter. So Lasse Warholt, I just wanted to know, so you mentioned briefly that, you know, we sort of see better performance for the self-supervised and for the latent variable models. That definitely seems to be the feeling that we get. But are there any other generalizations that we can pull out from your classification about what sort of strategies are more effective than others? Or even just for specific tasks? Like, are there anything, is there any other generalizations about what works?
So I think something that we tried to do initially with this overview paper was also to compare the results from the different papers, in particularly in terms of for the speech recognition task, which is probably the go-to evaluation task. But it's so difficult to compare these models. Of course, there's starting to come some kind of standard in terms of using the architecture, like the base large architecture for like Wouterbeck and Hubert and Data2Vec and these kind of models. But in general, I mean, it's difficult. But of course, the best performance is almost always seen with some kind of masking transformer-based architecture. I think that doesn't really come as a surprise for anybody. But yeah, it's hard to really draw any conclusions, because we cannot do a systematic comparison just by reviewing the papers like this.
Yeah. I mean, apart from the parameters that you summarize here, there's a lot of other differences between these models as well, right? So it'd be pretty hard to narrow it down.
Yeah, certainly.
I guess that's what you mean. Yeah.
Yeah.
Okay. That makes sense. Are there any comments or questions for any of the talks? Okay, I'll wait just a second longer, but just while we're looking to see if there's any other questions or comments, I'm going to wrap up the session. The session we'll take a 30-minute break after this. We will come back at 3:50 p.m. so 15:50 so in 30 minutes. Okay, and then we'll have the keynote from Jim Glass. Okay, so there's one more question. Okay, so great. We do have another minute for question.
Yeah. Okay. So I think it's for me.
Yeah.
So yeah, the question is, maybe I missed out, but could you comment on why you think models might or might not behave like humans in the way you measured? So the main difference between humans and models we found is the behavior at the level of contrasts. So it seems like there is a lack of invariance to contrast for the self-supervised models. We know that contrasts are important for humans. You've got like a specific discrimination behavior that is going to come up for a given contrast, but it doesn't seem to be the same for self-supervised models. And the reason behind that, so we have some ideas, but we didn't really explore them in details, but like my instinct tells me that it's probably because these models have a really short time scales, so they're going to predict at a really short time scale, and their representation frames are really at a short time scales. And as humans, to be invariant at the contrast level, we also have, in my opinion, we also have a representation that is, we do have a representation at a short time scale like these models, but we also have a representation at a larger time scale, and this is probably why we are so invariant to contrast and models are not. So yeah, it's not a complete answer, but this is like my opinion about that.
Okay, and with that, we are perfectly out of time. So thank you very much again to all four speakers. And go ahead and take a 30-minute break and come back here to see the keynote at 10 minutes to 4. See you then.